slow decline. It was a cosmic execution. In a single, horrifying moment, a rock the size of Mount Everest slammed into the Yucatan Peninsula, releasing the energy of billions of atomic bombs. Imagine that event happening today. Not 66 million years ago, but right now, above your head. Forget pandemics and climate change. The real existential question is this: if a 10-kilometer object were on a collision course, would humanity's sophisticated defense systems save us? Or would our complex global infrastructure simply crumble faster than the reign of the mighty Tyrannosaurus Rex? That is the chilling scenario we must confront. And the answer, counterintuitively, is that for all our ingenuity, for all our technology, the collapse of human civilization would be an event of catastrophic speed, potentially dwarfing the rate of extinction experienced by the great reptiles. The common notion is that we are the masters of our domain. We have satellites, telescopes, and the scientific knowledge to track these celestial assassins. Surely this gives us an edge that a lumbering triceratops never had, right? I know what you are thinking. The dinosaurs were victims of a blind, uncaring universe, but we would see it coming. That is the thesis that the current science of planetary defense completely contradicts. The terrifying conclusion is that while the dinosaurs were extinguished over a period of months and years by the resulting environmental collapse, humanity's functional extinction, the total dissolution of civilization, could be measured in mere days or weeks. Why? Because the nature of our vulnerability is fundamentally different. The dinosaurs were a biological system, a food chain, and a collection of species that needed to adapt to a new, hostile climate. Their extinction was a process of starvation, freezing, and failure to reproduce in the poisoned aftermath. We, however, are a technological system. We rely on a global tapestry of just-in-time logistics, interconnected power grids, and a digital nervous system that spans the globe. Look closer at this system. It is robust in the face of local failure, but exquisitely fragile in the face of a simultaneous global shock event. The Chicxulub impactor, estimated to be around 10 to 15 kilometers wide, struck with the force of approximately 100 million megatons of TNT. The immediate effect was not just a hole in the ground. It was a seismic shockwave that wrapped around the entire planet multiple times, triggering massive earthquakes and volcanic activity globally. Within the first hour, a mega tsunami, hundreds of meters high, scoured the coastlines of the Proto-Caribbean and the Gulf of Mexico. But the real killer, the event that defined the KPG boundary, was the atmospheric collapse. The sheer heat generated by the debris ejected into the atmosphere caused a global firestorm. Imagine the planet being briefly turned into a convection oven where everything flammable, every forest, every patch of dry grass, ignited simultaneously. For the dinosaurs, this meant the immediate incineration of vast swathes of life and the collapse of the primary producers, the plants that formed the base of their food pyramid. The long-term killer was the impact winter, caused by colossal amounts of dust and sulfates blocking the sun for years, plunging the Earth into a brutal, dark cold. The dinosaurs were resilient in a biological sense. Some smaller species and avian lineages survived the initial blast and the long night. Their bodies were tough, and their metabolic rates, while high for the largest beasts, allowed them to persist in niches. But now, look at us. Our resilience is a myth sustained by continuous power and communication. If that same object struck the Earth today, the initial seismic waves would instantly shatter critical infrastructure. Oil pipelines, nuclear power plants, dam walls, and the fiber optic cables that are the very veins of the global internet. The electrical grid, which is already prone to cascading failures from simple storms, would be immediately destroyed by the electromagnetic pulse and the physical shaking. Within 24 hours, the financial markets
Look at the
would
red
cease to
line.
exist.
We are running out of time.
Within 48 hours, every major city would run out of fresh, clean water, as the pumps that bring it from reservoirs rely on constant, uninterrupted electricity. I know what you are thinking. Surely we have backup generators. But generators require fuel, and the delivery of that fuel relies on roads and ports that would be choked with debris, and a transportation system powered by a grid that is now dark. The extinction of the dinosaurs was a geological and biological event. The extinction of humanity would be a societal and logistical one. The dinosaurs starved slowly in the dark. We would riot quickly in the dark, and then starve just as slowly, surrounded by the ruins of a complex system we no longer know how to operate. This brings us to the crucial difference: the timeline of worldviews and the nature of the threat itself. For millennia, human civilization viewed cosmic impacts as the domain of myth, the fiery judgment of angry gods. The Sumerians, the Greeks, and the Maya all had stories of celestial destruction, but they were stories of inevitability, not of science. Even when the first modern scientists, like Georges Cuvier in the 17th century, began to propose the idea of catastrophism, that Earth's history was shaped by sudden, violent events, the idea was fiercely resisted. The dominant paradigm, uniformitarianism, suggested that geological changes were slow, incremental, and observable. The idea of an instantaneous global killer from space was, until the mid-20th century, considered fringe science. It took the discovery of the iridium layer in the late 1970s by Luis and Walter Alvarez, and the later identification of the Chicxulub crater to force a paradigm shift. We finally accepted that our existence is precarious, living on a cosmic shooting range. The dinosaurs, in their time, were simply living in the moment. They were the apex predators of a stable world, completely oblivious to the celestial mechanics that governed their fate. Their worldview, if we could anthropomorphize it, was one of constant local struggle for survival. They had no concept of an impending extraterrestrial threat. Our worldview, however, is one of constant, global vigilance. We have dedicated programs like NASA's Planetary Defense Coordination Office and the infrastructure to track almost every near-Earth object, or NEO, that passes close to us. We are armed with this knowledge, this global awareness, which should theoretically give us the ultimate advantage, the ability to intercept. But what happens when the very thing that gives us an advantage, our technology, is rendered useless by the nature of the threat? This is where the conflict between the models of survival truly emerges. The dinosaurs' brute biological resilience versus humanity's fragile technological
Look at the
complexity.
stress fracture on the manifold.
Let us
I see
model
it.
the vulnerabilities.
Adjusting the parameters now.
The dinosaurs, particularly the large sauropods and theropods, had a major weakness: their scale. They required immense amounts of food and had long gestation periods. When the primary food sources vanished, they had no way to quickly adapt or reproduce their way out of the crisis. However, their structure was simple. A hungry dinosaur could still function as a biological entity, searching for food in the ruins. They did not need a power grid or a functioning sewage system. Humanity's vulnerability
Stew is almost
the
ready.
opposite.
Good,
We
the
are
panels
small,
are charging well
adaptable,
tonight.
and quick to reproduce. Biologically, we are survivors. But we have traded that pure biological resilience for the comforts and necessities of civilization. We have built a system where 90% of the population lives in dense urban areas, relying on food shipped in from hundreds of kilometers away. This is the key difference. The dinosaurs' extinction was driven by a food crisis. Ours would be driven by a systems crisis. Imagine the impact occurs. The initial blast kills hundreds of millions instantly in the affected hemisphere. Within hours, the global economic system, the system that allows a doctor in London to eat an apple grown in Chile, ceases to exist. This means that the billions of people who survive the initial impact, the people living in Africa, Asia, and the Southern Hemisphere, are suddenly cut off from the global supply chain that feeds them, heats them, and keeps them safe. The death toll would not be from the impact itself, but from the cascading failure of the systems that sustain our population density. The human extinction timeline accelerates dramatically because of this technological dependency, making us functionally extinct as a global civilization far faster than the dinosaurs were as a biosphere. But we must ask the critical question: what object exists now that could cause this level of global devastation? And what specific failures would have to occur for it to slip past our advanced defense systems? We are not talking about small space rocks. The Chicxulub impactor was a monster, estimated at between 10 and 15 kilometers in diameter. Our current defense systems are very good at tracking the vast majority of near-Earth asteroids, or NEAs, especially the ones that orbit primarily between Mars and Jupiter. The most famous of these, like the asteroid Apophis, are well tracked and, after careful analysis, have been deemed non-threatening for the foreseeable future. However, the greatest existential threat comes not from the well-behaved asteroids in the main belt, but from the rogue, long-distance travelers. I am talking about the long-period comets. These are the icy bodies that originate far beyond the orbit of Neptune, in the Oort cloud, a spherical shell of icy debris surrounding the solar system. These comets can take hundreds or even thousands of years to complete a single orbit. Because they spend 99% of their lives in the outer darkness, they are incredibly difficult to detect until they are already inside Jupiter's orbit. Look at the mechanics of the threat. A typical long-period comet can be traveling at speeds of 70 kilometers per second, significantly faster than an asteroid. If a 10-kilometer comet from the Oort cloud were gravitationally perturbed and sent hurtling toward the inner solar system, we might only have a window of a few months, or perhaps even just a few weeks, to detect, confirm, and react. This brings us to the critical failure point, the moment of paradigm rupture. Our entire planetary defense strategy is built on the assumption of years of warning time. We have developed missions like DART, the Double Asteroid Redirection Test, which successfully proved we can nudge an object's trajectory. But the DART mission required months of preparation, launch, and travel time to impact a relatively small, non-threatening asteroid. Now, imagine the scenario. A massive 10-kilometer long-period comet is detected by a survey telescope like Pan-STARRS or Atlas. The calculation is immediate and terrifying. Impact confirmed for Earth in 8 months. This is the point of no return, where all our scientific knowledge collides violently with the reality of physics and logistics. What has to fail? Everything. First, the detection fails. The comet is coming from the direction of the sun, or at a high inclination angle, making it invisible to our primary survey telescopes until it is too close. The 8-month window shrinks to 3 weeks. Second, the decision fails. The world's governments, paralyzed by the sheer magnitude of the threat, cannot agree on a unified, instantaneous response. The clock is ticking, and the world is already descending into chaos. Third, the deployment fails. There is no existing pre-built nuclear device or kinetic impactor powerful enough and fast enough to intercept a comet traveling at 70 kilometers per second and change its trajectory in 3 weeks. We have the theoretical ability to deflect, but not the practical deployed defense mechanism ready to launch at a moment's notice. The old model, the idea that our technology makes us immune, shatters. The new, terrifying reality asserts itself. We are just as vulnerable as the dinosaurs, only our downfall is more spectacular and faster. The paradigm rupture is complete when the comet enters the atmosphere. The pressure wave alone would flatten forests and structures over a massive area. The impact site becomes an instant, glowing caldera of vaporized rock. The resulting global firestorm, triggered by the superheated debris raining back down, would not just consume the world's forests, but also ignite every single oil refinery, gas tank, and chemical plant. The air would become toxic, a mixture of carbon dioxide, sulfur compounds, and soot. The very infrastructure that allowed 7 billion people to thrive, the interconnected energy and transportation networks, becomes the accelerant for our doom. The dinosaurs survived the initial impact with their biological systems intact, only to face a years-long ecological crisis. They were victims of a climate change event. We survived the initial impact with our biological systems intact, only to face an immediate, total collapse of the support systems that allow us to live in such density and complexity. We would be victims of a systems failure event. The legacy of the dinosaurs was the quiet, slow re-emergence of life in the following millions of years, leading to the rise of the mammals. The Earth became a blank slate, cleansed of the massive reptilian rain. But what would be the legacy of humanity? The aftermath of a modern impact would be fundamentally different. We would leave behind a toxic, radioactive graveyard, the collapse of hundreds of nuclear power plants, chemical storage facilities, and industrial complexes would release a cascade of pollutants that the dinosaur extinction never had to contend with. The impact winter would be followed by a prolonged period of intense radiation and chemical contamination. The new enigma is not just how to survive the impact, but how to survive the ruins of our own civilization. The research continues, driven by the chilling knowledge that our current systems are simply not fast enough to handle the true existential threat. Projects like the Sentinel mission, which aims to place a telescope in orbit to detect
Mission
NEOs
control,
closer
we have
to
contact.
the
The
sun, are
object
the next
is
logical
accelerating.
step. We are trying to buy back the warning time that a long-period comet threatens to steal from us. We are also exploring the possibility of hyper-fast interception methods, rockets that can be launched within days or even hours of detection,
The projections are
carrying
worse
kinetic
than anticipated.
impactors, or in a truly
Look at the red
desperate
lines. They're
scenario,
crossing the
nuclear
threshold.
devices tailored for deflection. But the core challenge remains. The faster the threat, the more centralized and automated the defense must be. Do we, as a global species, have the wisdom to delegate the power of planetary defense to an automated
interceptor
system that
missed.
could, in theory, launch a nuclear weapon into
accelerating.
space based
Impact
on an
in
autonomous
T-minus 10
calculation?
seconds.
It's getting closer.
That
Move.
is a political and ethical
Look at
enigma
the sky.
as complex as
Oh
the
God,
physics
run,
itself.
It's right above us.
The comparison between the two extinctions is a grim lesson in evolutionary trade-offs. The dinosaurs traded intelligence for brute biological scale, and they were undone by a slow-burn ecological crisis. We traded biological scale for hyper-complex intelligence and technological dependency, and in the face of a cosmic threat, we would be undone by the blinding speed of a systemic collapse. The dinosaurs took months and years to truly vanish. Humanity's reign, as a functioning global entity, could be over in a matter of weeks, leaving behind a technological graveyard for whatever life form inherits the Earth next. The real question is not if the universe will send another killer rock our way, but whether we can build a system of defense that is faster, more decisive, and less fragile than the civilization it is designed to protect. Until then, we live on borrowed time, a sophisticated species in a very fragile house, forever looking up at the dark sky, hoping the next light we see is not the one that ends us.